This conference will now be recorded.
Just a reminder to those, you may have just heard that, but we are recording these sessions. They will be put on with links to from the NOPP website sometime in the future, probably in the August timeframe once we've concluded all of the sessions. All right, we're at the top of the hour. We've got people rapidly joining, up to almost 60 now. So I just want to thank everybody for joining us today for the continuing series focused on the NOPP Hurricane Coastal Impacts project. Alex Kripov can't be with us today, but I did want to thank him and the group for letting us piggyback on their normal seminar series over the last few weeks and for the balance of this month every Tuesday. My name is Alan Leonardi. I'm the director of the National Oceanographic Partnership Program Office, or NOPP as we commonly refer to it, and I'll be your MC and your moderator again today. The NOPP Hurricane Coastal Impacts project that will be discussed as part of the series, they're supported by the National Oceanographic Partnership Program with primary funding from the Office of Naval Research and the National Oceanic and Atmospheric Administration. Today's discussion is the third in the 5-part series and will include 2 presentations. The first presentation, which will be given by Jim Thomson and Jacob Davis from the Applied Physics Laboratory and Isabel Houghton from Sofar Ocean, will focus on buoy observations of wave spectra and hurricanes, including specifically those from aerial deployments of wave buoys. The second presentation will be Martha Schonau of the Scripps Institute of Oceanography, focused on observations of directional wave spectra from a sustained and targeted Lagrangian director array. Now, normally we would have each presentation last about 30 minutes, including a 10-minute question and answer period. But given the complementary nature of the talks, the presentations will be given back-to-back today with questions for all speakers at the end. So for ease of discussion using this virtual format, I ask that you refrain from asking questions until the end of the presentations, where I will go through the process and attempt to moderate a Q&A. I'll now hand the virtual microphone over to our first set of speakers to get the conversation started. Jim, the floor is yours.
Great, thank you, Alan. We want to thank NOPP for the support of this program and thank everyone for attending and really appreciate this series to tell everyone what we've been up to. We are still in the thick of this program where we'll be making more observations this year and continuing on. I will start this presentation, and then Jacob Davis is a PhD student working on this project. He will continue with the middle slides, and then Isabel will close out our slides, and I'll just keep advancing for the team as we go. So, buoy observations of wave spectra in hurricanes. We are interested in waves and hurricanes for a whole bunch of reasons. Probably most of the audience is familiar with some of these processes, but I'll just recap them here. First, the waves are the central process at the air-sea interface, and that modulates the exchange of heat and moisture, which is really how a hurricane is fueled. So if we'd like to understand the exchange coefficients and the drag coefficients that are so important to getting forecast models, to a really skillful level, we need to understand what the sea state is in a hurricane. And the sea state in a hurricane is very complicated, right? There's different quadrants of the storms where winds and waves are aligned or misaligned, and you can see these pictures of the ocean surface here. It can be a very complicated and confused multi-phase flow in which that exchange is occurring. So that's one reason to study waves in hurricanes. Another reason is just very practical. The waves endanger ships and cause damage to infrastructure. And then when we get to the coast, because this project is really focused on the coast, waves contribute to the storm surge and flooding at the coast. So we'd like to understand and be able to better forecast the waves that will arrive at the coast and add to that flooding. Historically, and we got a little bit of background noise there. Can we get a mute? Thank you. So historically, waves in hurricanes are difficult to measure because hurricanes are relatively compact. The radius of maximum winds might be 100 kilometers, something like that. And so if you look at the NDBC moored buoy arrays, or if you look at the CDIP arrays or other existing arrays, they're actually too sparse to really capture all these details. So hence, we've taken a more targeted approach to get these kind of measurements. Here are just a few continuing examples in terms of motivating why to do this study. Here's a publication from Dietrich et al. Looking at Hurricane Katrina and talking about the wave-driven components of setup and the surge that occurred at the coastline here. So these contributions are in the order of 1 meter that the waves are adding in addition to the other processes, the wind-driven setup and the inverse barometer effects. So this is part of understanding coastal flooding and predicting coastal flooding is getting the wave-driven part correctly. And then over here, the second plot is one, this is very recent work from a master's student and a US Coast Guard officer that was working here in our group, and he was looking at infrastructure damage during the recent Hurricane Ian and the 22 storm that hit Florida. And he was looking at the likelihood of damage of Coast Guard aids to navigation as a function of wave height. And you can see that that this is a pretty skewed distribution. The really big waves have a very high likelihood of damaging the Coast Guard aids to navigation, which then the Coast Guard has to go out and fix immediately afterwards for safe navigation. So these are just, continued motivation for studying waves and hurricanes and being able to improve their forecasts by making targeted measurements. So our targeted deployments have been mostly aerial deployments. So here's an example of the spotter buoys. So these are commercially produced buoys by Sofar Ocean, and Isabel is the co-PI from Sofar who's providing the buoys and helping us work with the data. We have been putting out anywhere from 10 or more of these through the open door of a P3 aircraft. This is not the Hurricane Hunter P3 aircraft that NOAA flies. This is a P3 that the Navy flies out of Pax River, and they are very familiar with open door deployments. They use the open door for doing aerial deployments of aid packages, of sauna buoys, all sorts of other things. So when we engaged with them and asked about doing this, they were very ready to help and had lots of recommendations on how to outfit these buoys to go out the door. They do not have a parachute. They just free fall. They free fall upright due to the drag that's added with these cardboard sleeves, and then the cardboard sleeves fall away once they're in the water, and they survive the drop just fine. So I think it's pretty spectacular that we started this project. Somebody said, well, why don't we just throw them out and see how they do? And they do just great. So those are the spotter buoys. We have other buoy types as well, and that's one of the fun things about this project is having lots of different buoy types, which all have different advantages and strengths and weaknesses that kind of complement each other. So the other buoy type are the micro swift buoys. We make those here in our lab at the Applied Physics Lab at the University of Washington. They're smaller than the spotters. You can see them here, and they have this cylindrical or tube shape. They can go out of the open door. There's Jake putting one out of the open door, but they also can go out of the dropson tube. So here's a picture of testing, putting it through the dropson tube, and this provides more opportunities for deployment. If an open door is not possible, then we can go out of the tube. And here's a little animation of one of them coming out of the tube of a NOAA aircraft, and then you can see the chute deploying just behind it. So these do have a chute. They are also packaged in cardboard, which falls away once they're in the water. And we have either deployment method available. The third buoy type you'll hear about in this the talk that immediately follows, and Martha will tell you all about the ADWSDs that her group deploys that rounds out this fleet of buoys. So those are the buoys, and here's a little bit of an example of the kinds of things we've done. This is in Idalia last year, the end of August in 2023. This was the storm that came across the Gulf and then hit the Big Bend region of Florida. And if I could be not so humble as to say, we really nailed it with this one. I think we laid out an array of buoys that were across all 3 buoy types that were really able to make these measurements of the wave field of the storm as the storm came through, that were really populating all the quadrants of the storm, not just seeing one part of the storm, but seeing in a synoptic, coherent way how the waves are different across different sectors of the storm. So here's the array itself, all these different symbols here, and then here's the satellite image of the form of the storm as it passes over. And then here's one particular example of what a buoy sees, what an individual buoy sees. It of course sees a significant wave height ramp dramatically as the storm comes over, in this case peaking at 7 or 8 meters. I think we've seen up to 10 in some other examples. This is a spotter buoy, which also measures the sea surface temperature and the barometric pressure. And so you can see the SST dropping and the cold wake after the storm passes. And then you can see as the eye comes over, you can see this pretty dramatic drop in the barometric pressure down to almost 950. So the waves have been the focus of the program, but there are these nice ancillary products as well. And again, these were all aerial deploy 2 days before the storm passed. So the storm was down here. We rapidly mobilized the team in Pax River, and the Navy P3 came out and put these all out. Meanwhile, the NOAA P3 was down here sampling the actual storm as it made its way up, and then the buoys were still in place, drifting around. They drifted a little bit before the storm came across, but not so much as to really deform the array. So they were still pretty well in position as the storm came across, and we got these nice measurements. Okay, at that point, I'm going to hand off to Jake, and he'll tell you a little bit more of the more detailed science that we're doing with these, and I'll keep advancing slides for you, Jake.
Great, thanks, Jim. So hi, yeah, I'm Jake. I'm a graduate student at the University of Washington. I'm working with Jim and Isabel on this project. And so some of the science questions I've been tackling, as part of my dissertation and this project, have related mostly to wave slopes and hurricanes. And so when I mention the wave slope, I literally just mean the geometric slope of the wave. So for example, the ratio of its height to its length. The reason being is that wave slope has proven to be pretty essential in the parameterization of deep water braking processes, for example. So in this bottom right-hand picture, that is a wave that has gotten too steep and it's just about to break. Wave slope has also been shown to be a proxy for roughness, and has also shown to correlate with form drag, which is an important component of drag in hurricanes. And so some of the questions we've been trying to tackle and address are, one, how does wave slope behave at hurricane wind speeds? A lot of work has focused on sort of these lower wind speed regimes, sort of less than 20 meters per second. So asking the question of how does it behave, at 30, 40, 50 meters per second, close to the storm? And then also, how does wave slope vary spatially within a storm? And so next slide, please. And so that first question, we were able to take a look at with the help of one of the data sets we collected during the first year of our deployments. So on the left, you're looking at a map of the Florida region, and then the red dots show the track and intensity of Hurricane Ian. And the yellow pentagons there just show the spotter buoys. We deployed other buoys, but I used the spotters just for this particular data set. So it's the positions of the spotters, mostly in this case on the left side of the storm. And the little inset in the bottom left shows one of those spotters in the context of the COAMS TC wind speeds. COAMS TC is one of the forecast models from NRL that we've been working with on this project, and give us wind fields to co-locate with the buoy data. And so what we've done is we've taken that wave buoy data. In this case, we've calculated the mean square slope, which is can be derived from the fourth moment of the spectrum in the case of a frequency spectrum. And on the right-hand side, I've plotted the mean square slope as measured by the buoys versus the 10-meter wind speed from the model. And what we find is that in wind speeds of less than 20 meters per second, the mean square slope is approximately linear with wind speed, which is has been reported from a lot of other data sets and instruments. But what we find that's really interesting is that these higher wind speeds in hurricanes, above about 20 or 25 meters per second, that sort of undergoes a regime change where the mean square slopes increase a lot less for increasing wind speed. So it sort of approaches this quasi-saturation. We think that's significant because if the slopes are saturating and they are then correlated with roughness and form drag, that could mean that those two variables are also decreasing, and then in turn impacting the intensity of the hurricane. So that's some work that we published as part of the first chapter of my dissertation in GRL last year. And then on the next slide, please. And then with a data set from Hurricane Idalia, which Jim had showed on a couple slides ago. In this case, we were able to have a much more dense array, sort of buoys on both sides of the storm at the same time, and sort of paint this picture in the storm following reference frame. So first on the left, I'm again showing the mean square slope measured by those buoys in Idalia, again versus COAMS TC 10-meter wind speed. In this case, when we sort of classify the data set or classify the observations by whether the wind and waves are aligned, meaning that they're both traveling the same direction, or in this case, crossing, where they're sort of perpendicular to one another, that it has a pretty substantial effect on the magnitude of the mean square slope at least as a secondary dependence of mean square slope. So then on the right-hand side, now I'm showing the buoy observations as each of these dots, the colored pentagons and purple circles show the initial position from our ray and Adalia, and then I'm sort of showing the relative position to the storm, with the storm at 0, 0, always pointing up. As the two sort of intersect each other, we can sort of, so we can trace out the spatial map. And here I am showing each of those observations that make up the left-hand plot, but in this case, I am again classifying them by whether they are aligned or crossing. There are no instances of opposing waves, but I've also added that in the scale. And what we see is that, generally speaking, the aligned waves fall sort of to the rear and to the right of the storm, which would then suggest that the mean square slope would be amplified, sort of in that quadrant or in that part of the storm. So this all sort of ties together to suggest that not only does mean square slope have a dependence on wind wave alignment, but that it has this distinct spatial distribution within the storm. So slopes are elevated where wind and waves are aligned. And so next slide, please. And so tying this all together, using these data sets collected, these buoy data sets collected as part of the NHCI project, we've been able to show that the saturation of wave slopes, or rather that the wave slopes saturate with high wind speeds, which is qualitatively consistent with what's been shown for drag saturation. So for example, on this bottom left plot, this is showing several different drag observations and parameterizations, and showing that at some wind speed, most of them seem to have a tendency to sort of saturate above 25, 30 meters per second. So we're seeing something very similar in wave slope, and given the connection of wave slope and, for example, form drag and roughness, there might be a possible link between the two. Also, wave slope and drag both correlate with wind wave alignment. There's been some recent work by several authors, but for example, on the bottom right, I'm showing a plot from Zhao et al. In 2022, showing that drag coefficient versus wind wave alignment on the x-axis, the drag coefficient is highest when the wind wave alignment is small. So for example, the aligned case, and then as that alignment sort of increases as the wave and wind become more misaligned, that drag coefficient decreases. And so we're seeing a similar trend with mean square slope. And then the big picture is that capturing these physics and working with modelers and forecasters on the team, that we can help move the community towards a sea state dependent drag parameterization, one that's dependent on wave slope, wave age, and also wind wave misalignment. So those, so that's my slides. Thank you.
Cool. Thanks, Jake. I'm Isabel Houghton. I'm a research scientist at Sofar and co-PI in this project, really working with providing the spotters and working with that data as well. So I thought I'd add some additional context on how these observations can be used, in addition to some of this basic physics research and parameterizations by Jake, and then also the forthcoming talks, really thinking about how these observations are critical for model ground truth comparison. But kind of looking forward and kind of zooming out as well, there's a lot of broader real-time use in being able to get rapid response targeted deployments into storms. And this comes in the form of data assimilation. So if you go to the next slide, I'll spend the last couple minutes that we have talking about how data assimilation can be utilized to really impact your wave forecast skill. So the schematic here is what we do at Sofar in terms of our wave forecast and data assimilation cycling. And this can be generalized quite broadly, in that you largely just need a background initial condition, running some model, in this case working with WaveWatch 3, but within the NOPP project also can be a coupled model where you have atmosphere, wave, ocean, or some other setup, and that feeds into a data assimilation scheme. What I'll talk about, or the results that I'll show here, are from a development of optimal interpolation, where you're effectively just trying to best fit your observations that you have with your model background, and that yields an analysis field that you can then use to run a forecast. And the idea here being that if you can initialize your forecast with your best estimate of the current conditions, you'll have a more accurate forecast several days out. And we know that there are quite large departures or differences between observations and, say, a model state as you're trying to initialize. And so any observations can be really critical in improving your skill. Next slide. And something really unique about all of the buoys that we're deploying here is that they're actually directional wave buoys. So historically within wave modeling and assimilation, you're really limited by satellite observations, and those largely observe significant wave height. But what's shown here is just a tangible example of a buoy south of Florida as Hurricane Ian was developing. And on the right is a plot of the variance density spectrum generated or estimated from the directional moments from the buoy. And this is just to give you kind of a qualitative understanding of the distribution of energy, both in direction and in space. And as you can imagine, properly capturing that in your wave model is really critical for your future forecast skill, particularly in these situations where you have such high variability over a small area. Next slide. So within our data assimilation at Sofar, I thought I'd show here just a global example of the impact of having observations within a wave model. And so every marker is actually a spotter buoy. And what's shown is the difference in wave height with data assimilation versus without. And you can see these large scale differences on the order of 3/4 of a meter to a meter. A couple of artifacts from a satellite observation passing over as well, which we include. And this is really just showing that even just correcting for the energy, we're not showing the peak period yet or anything like that. Having observations really does modify your forecast. And as Jim mentioned in the beginning, correctly forecasting your wave heights has a lot of implications broadly. Next slide. If we try and also just quantify the impact to skill, what's shown here in the gray line is a normalized aggregation of skill in significant wave height, either in sea or swell. So the left two plots compared to a model without data assimilation, using assimilation just with the bulk significant wave height, and then assimilating information from the directional wave buoys. And I just put the publications down there if you're more curious about the specific methods, how we integrate information about energy as a function of frequency and direction. But as you can see, in particular for the swell height, where you could expect if you can properly initialize your swell, it really just becomes that initial value problem and propagates out. And so that has a good amount of impact. And then also you can see it in something like the peak direction on that rightmost plot, where particularly in the early times, we've really much more accurately captured that peak direction. And once again, as I think the modelers will speak to, things like capturing the incoming wave direction is a very important boundary condition to their coastal models. Next slide. So I'll hand it back to Jim to wrap up here, but as I mentioned, just a forward-looking outlook on how observations can be used across all these different applications.
Thanks, Isabel. Yes, I just wanted to let everyone know, I imagine you've already heard through the series that we've been focused on hurricanes Ian 2022, Idalia 23, Lee, less so in 2023, but we did sample that storm. And I think it makes sense to just hand over to Martha now for talk about the rest of the buoys.
Okay, thank you. Thanks, Jim, Jake, and Isabel. So as everybody see my screen now? Yep, okay, just making sure before I keep going. Yeah, so as I said, this is observations and more observations. So my name is Martha Chernow, and I am an assistant project scientist with the Lagrangian Drifter Laboratory at the Scripps Institution of Oceanography. And this is work done together with Luca Centurioni, the director of our lab, who unfortunately had field work today, so couldn't be presenting. And so what the work we do here is, complements and adds on to that of Jake, Isabel, and Jim. And, we come with our own instruments as well. So I'm going to talk about the instruments we do and some of the analysis that we've done in these hurricanes. So shown here is the VXS1P3. And then our A-size directional wave buoy in the middle is slender, similar to the microswift. That washed up on the beach after we deployed it in Cape Cod during Hurricane Lee. There's an image of Hurricane Idalia, and then our full-size directional wave spectra drifter with a barometer that washed up following Hurricane Idalia. Luckily, we were able to get both of these drifters back. So the Lagrangian Drifter Laboratory, these are just a few of the drifters that we make. The lab is part of the Global Drifter Program in collaboration with AOML, and we provide all of these drifters to the global ocean. The most common one is the Surface Velocity Program Drifter. Those have drogued. Now I'm showing here the directional wave spectra drifters. It's the same hull that's on the Surface Velocity Program, or SVP drifter, but it doesn't have the drogue. And then here is our A-size directional wave spectra drifter that was developed to fit through that chute of the P3. Just makes it easier to deploy from different aircraft. Here's the array over the global ocean, but of course today we're going to talk mostly about our efforts for observations under hurricanes and helping get these outshore wave conditions for wave models and coastal storm surge models. So at the lab, we want to study all processes, between the ocean atmosphere along the global ocean surface. We make these observations available typically to the global telecommunication system to improve numerical weather forecasting. But these are the different ways that we study hurricanes. Hurricane both below the ocean and above. So there's airborne observations. You typically see, the hurricane hunters putting out expendables, taking, satellite observations, but there's fewer surface observations. And so many people ask, well, why drifters? I think as Isabel and Jake and Jim already made the case, is they're easy to deploy, and they're also cost effective. You can get them in the right time in the right place, and they're on the surface as opposed to below or above. But they're also very dynamic. We can configure them in different ways. And for our drifters here at Scripps, we use two-way iridium communications, which allows us to change the sampling rate as we go. So if there's no storm, we can put it into a low power mode. If we see a storm coming, we can up the sampling rate, to 30 minutes and have this adaptive sampling going on. So as I mentioned, we have two types of drifters. We have the A-size drifters that are deployable from a P3. That's the bottom of the NOAA P3. But we have been deploying drifters into hurricanes before that, typically with 53rd Hurricane Hunters. So out of the back of a C-130, we push a big package of a wave drifter along with a mini MET drifter, which has a sonic anemometer. So the first hurricane we targeted with wave drifters was Hurricane Michael in 2018. There's a recently published paper on that, as well as Hurricane Isaias, Hurricane Teddy. But of course, as Jim mentioned, the ones that we've gotten during the NOPP program are Hurricane Ian, Hurricane Idalia, and Hurricane Lee. And today I'll show you mostly results from Hurricane Ian and Hurricane Idalia. But since 2018, we've had a lot of success in deploying wave drifters specifically to target hurricanes, as well as our mini MET drifters I mentioned, which actually take surface wind observations. So the drifters measure directional wave spectra using GPS technology. So this is similar. I don't think Jim and Jake and Isabel mentioned this, but it's basically delivers the first five coefficients, the energy and the directional moments, and that's similar across all the drifter types, the microswifts and the spotter buoys. Our drifters have temperature, which I believe a few of the other drifter types do. We have an optional barometer, and this data is available in real test. We can optionally put it up to GTS, which we like to do for weather forecasting, and we also deliver it on our ERDAP server. So this was a drifter deployed in Hurricane Ian, and this is kind of what the observations might look like. We're also comparing these, in real time to, say, ERA 5 or WaveWatch 3, publicly available observations. You can see significant wave height, peak frequency, average frequency, dominant direction. So just general, we call these the bulk parameters. So how do we actually target these hurricanes? Well, I see everybody knows hurricane seasons are different, right? We can't just put out the drifters ahead of time, but we don't always have those assets. So the first thing that we do is often at the beginning of the season is we put out a sustained array. As Isabel mentioned, there's sometimes a lot of just getting the drifters out there. You'd be amazed what you might observe. So at the beginning of the season, we put out the sustained array. We also have adaptive sampling to increase the observation rate. And then we also can target extreme events. And so shown here is, the efforts that we did, and I won't spend too much time on this because they already showed it. I do have a video of the we can put them out the door. We've put the A size out the door as well. Here is a very loud video. Sometimes it's much easier. Just to put them out the tube at the bottom of the plane. You don't have to open the door. So this is why, and so the micro swift, they didn't show the video, but it's identical. You just put them out the tube at the bottom, and it's pretty easy. So I'll start with Hurricane Ian. Jake already showed some observations from Hurricane Ian. I'm just showing that 80 WSDs, those are the ones I tend to analyze the most. But with Hurricane Ian, we use this, use the strategy. We had a sustained array. We had some drifters out. This was in 2022. And this is kind of how we put together the array prior to a deployment. So we had 3 drifters that were out that were in low power mode. And so we saw Hurricane Ian coming. We increased the sample, we turned them on, increased the sampling rate. NRL laid a line of 5 80 WSDs, and Jake got to go on those flights, so he took these photos right here. These are just the 80 WSDs. There was actually a much bigger line with the microswifts and spotters. We also deployed with the 53rd on our side some of the wind drifters along here and a few more wave drifters, and then added some with a helicopter up north. So it really is kind of a big operation, to get all these drifters in the water ahead of time. And these are just the significant wave height sampled from all of these drifters. You can look at a single drifter. This is what it might look like from WaveWatch 3. And so you can see what we try to do is see where are the models perhaps not seeing the same thing that the observations are. So for Hurricane Ian especially, we have this huge hurricane coming on shore, and the models in general, things like WaveWatch 3, well, this is publicly available WaveWatch 3, underestimated the peak. But we actually saw this sometimes in the coastal surge model that other NOPP collaborators were running. And so it's useful to have these ground-based observations. We actually had a wind drifter in there. We measured a peak wind of over 120 miles per hour. But we can compare these again to what our collaborators in NOPP, Jim and Will Kamarami, when he was with NRL at that time, had provided. And you can see this really good, interesting comparison of this mini-met that almost, we think, went right through the eye wall of the storm. So what I've been working on as part of my analysis is just to map all of these things into storm center coordinates. We're starting to be able to put these out ahead of a lot of storms. Before we had maybe surface observations, just during these large field campaigns. But now it's kind of exciting because I think we've shown that, during the hurricane season, we can really do maps of the wave field across any storm that we're targeting. So this is taking these drifters. It's just, again, the 80 WSDs that I'm using here. You can map out what the wave height is in storm center coordinates. So you basically average in 50, each square is a 50 by 50 kilometer bin, and you can see that the wave height ahead of the storm is small, and so it's kind of centered around, and then you get these really large plus 12 meter waves right ahead of the storm, and it falls off. Now I've put the date on the side because really what this is it's an average over space and time, right? The storm moves over the drifters, and this is the average time of, where you are measuring in that storm. But it kind of gives you the synoptic map of kind of where, how these storms vary in each quadrant. Front right quadrant, front left quadrant, and so on. So I'm going to second what Jim said. With Hurricane Idalia, we really nailed the observations. Again, I'm only showing the 80 WSDs, but you had seen before the combination of micro swifts and spotters that were also part of our array. With the 80 WSDs, we actually lucked out with our sustained array because we had about 4 of these NOAA buoys kind of float right into the path of Hurricane Idalia right as it was coming over the tip of Cuba. And so we could actually map these different wave height. We had some deployed by VXS1 from NRL and then Timberview. And you can see as it's coming over, we measured, wave heights is actually not 7 feet, 7 meters, 4 to 5 meters near Tampa Clearwater, and then about 9 meters just before landfall. So you can see this is a map again of the significant wave height with respect to storm center. It was different than Ian. The waves weren't as strong. We had much more energy on the right side. Probably a lot of that is water getting pushed forward. And the whole idea is to be able to look at these maps of the wave field and then use these to kind of provide a ground truth for these coastal storm surge models to see if they're getting similar wave fields in each quadrants of the storm. So as I mentioned, as you can see, Hurricane Idalia had a very different significant wave height field around the center of the storm than Hurricane Ian did, which was a much stronger storm. So a lot depends on, the size of the storm, the trajectory of the storm, and the radius of the storm. But significant wave height, we call that a bulk parameter, right? It's all the energy. It's the energy of the biggest 1/3 of the waves. So sometimes, in a wave field, when we talk about wind and wave coupling, it matters what kind of waves it is, right? There's long waves, there's short waves, and these really affect, the surface roughness, which Jake talked about, the momentum transfer. And so many people have looked out on the ocean and it's calm day, no breeze, and you can see these are the long swell, they kind of outrun the storm. These are long waves. They're not coupled as much with the atmosphere. They still provide surface roughness and wind waves right here. So typically we look at these in the frequency space. So wind C is at, these short choppy waves coupled with the winds at higher frequencies and the swell at lower frequencies. And integrating over the spectrum provides and scaling it provides that significant wave height I was showing before. And so what we're doing is breaking it down frequency space, because often in wave models, the spectra matters, whether it's, you're doing long waves or short waves. So it's just a better way of comparing to our wave models. So shown here is for Hurricane Idalia. So this is, say, a spectra, the actual frequency spectra from one of those drifters. And I've written frequency down here, but if you're not a wave person, you might not necessarily think in those terms. So, these are the, 20-second waves, 10-second wave periods, 5-second waves, kind of to give you an idea. And so what we can do, instead of making a map of significant wave height, we can kind of put it in those bins to see where the wave energy really was and how it might be coupled with the wind in these different quadrants of the storm. Because remember, in a hurricane, not only is it moving, the wind's turning in a circle, right, as it's moving northward. And so you might have different energy and different quantity in the storm, and these can then be compared to models. And we're working with some of the collaborators on NOPP to kind of see if the models have the energy in the right quadrants of the storm for those right, frequency ranges. But, as Isabel mentioned, what's also really important is the direction of the waves, right? Is that especially with these moving storms, what's generated in front of the storm is not necessarily what the storm has generated right now. And so you may have swell conditions going in one direction and high frequency waves coupled with the wind going in the other direction. So I like to make these arrow plots to kind of break that up. So again, these are the waves in the frequency bins. And I didn't put the periods of the waves, but this is low frequency, that's our swell, is in blue, and the red is that high frequency, coupled with the wind. And this is around the center of Idalia, so it doesn't have the area. Up is the direction the storm is going. But you can see that the red, which is the highest frequency waves, are more coupled in that cyclostrophic motion, whereas in some areas you can have these components of the waves going in different directions. This can lead to those conditions that Jake was mentioning, this crossing stream, the seas and stuff. And this varies, this can vary greatly depending on which storm you're in. I'm showing here, for instance, the paper that we already published on Hurricane Michael. You can see that in the rear quadrants of the storm, sometimes if there's some type of current interaction, or the storm is traveling very at a different rate of speed or stronger, you can sometimes have these components of the waves actually opposing in a very significant wave, and it can lead to a big decrease in the wave energy. And so some of the goals of this project is to understand how that might vary between different storms, and what it might mean for these parameterizations and models. So I wanted to leave plenty of time for questions at the end. Obviously, it looks like I did. But I just want to say that, on the fun side of things, it is a big effort to, deploy and get these out there. And then, we like to do the analysis at the end. I think hurricane field site season, we don't really spend much time on analysis. We just spend most of our time, tracking storms and getting them out there. A lot of these drifters that we've deployed, then we have to go and find and then redeploy. But it's actually kind of a fun thing. And so I really want to thank anybody in the audience who's helped us track down these drifters and redeploy them and get them back out there, because it really is becoming a group effort. So just as a summary, these hurricanes are unique in size, speed, strength, and trajectory. They can really different, which is why we think it's important to target each one. I think what we've learned with the group in collaboration with the modeling groups across NOPP is that each storm is different, and it's important to have these surface observations to kind of ground truth for the models. We've been doing a lot of model data comparison for that reason. So thank you, and I think I'll turn it over to Alan if he wants to lead the question and answer.
Great. Thank you, Martha. And thank you to all of our presenters today for their presentations. Extremely thought-provoking, and definitely helpful that there's plenty of time for questions for anybody who might want to ask them. If you want to raise your hand and ask a question, you turn on your camera and things of that nature, please feel free to do so. You can also place a question in the chat box, and I will try to get those in turn, and we'll ask the speakers to answer them however they might. And while we're waiting for folks to decide to start asking questions, and of course the speakers can ask questions of each other if they'd like, I did want to apologize. I didn't think that Alex was with us today, but he has been able to tune in. So Alex, glad you were able to make it. And we'll just hold the floor for questions for anybody who might want to have them. And in case you're wondering, yes, I will leave the awkward silence until somebody does actually ask a question if I need to. Jessica, I see you have a question, so feel free to unmute yourself and put your camera on if you want and ask your question. You're still muted.
Helps to turn off the mic. Sorry, turned off the camera, not the mic. I had a question. You spoke about comparisons with WaveWatch 3. And you were saying publicly available WaveWatch 3. However, WaveWatch 3 is a model. You can run it and configure it in a lot of different ways. So like it's not, when you were talking about WaveWatch 3, is that something like a model run you run? Is that a model that you grabbed from, like model output that you grabbed from somewhere else, or?
Sorry, I should have made that more clear. NOAA's Atlantic gridded WaveWatch 3. This was a download.
So from the GFS, from
probably from, yeah, from. I'll have to go look what we're using right now for those online comparisons, but yeah.
Because we have several wave models here at NOAA too, so.
Yeah, it's the ATLN. I think it was said it on, I'll have to go back and look at the slide to tell you. But yeah, I mean, I think I say publicly, because as you say, there's a lot of people developing WaveWatch 3,
Mhm.
doing unstructured grids and other things. And we were working with Ali Abdulali, who is, I think now at Army Corps of Engineers. So this was ATL OCN. I think that's one by GFS, I think. So I just wanted, some people look at that and go, oh, that's terrible. But I think partly it doesn't have the grid, for near shore for that one. And this is just, we have it set up on our website that we, pull in, probably not the best grid for coastal storm surge modeling, but, for open ocean comparisons.
Mhm.
So I think it would compare much better to, a model that's being run by NOAA. We actually don't run WaveWatch 3, we do observations
Okay.
only. So um, I'm always careful when I show things, comparisons to models, because, they are run differently. And folks often, I don't want to show a bad comparison and say that's what the model says, so um, yeah, it was WaveWatch 3 that was downloaded from a public site, not that we ran.
Okay. Thanks.
Thank you, Jessica. Other questions? And Martha, I'll just say that as classically trained as an ocean modeler, my model was always perfect in the absence of your wonderful observations. So it's good to have the combination of the two to actually see what's going on, to be able to do some testing and some analysis of what's happening. So, Young Gong, would you like to ask a question?
Yes, very nice talk. I like your comments, Ellen, your comments about we need more observations. Definitely, the nice observations. I see the huge difference in wind data as mirrored by this spar buoy versus those the two wind product. One's COAMs, the other's European Center ZPLOS. So as the huge differences. I'm wondering how you, because the spar buoy mirrors wind at the surface, basically the sea surface, but you were comparing the wind speed at 10-meter height. How you convert that from this surface to 10-meter winds? How and would that affect the cause the difference, or would that part have been considered? In what way you consider that? That's question for Martha, I believe. Yeah.
Yeah. So the mini-met drifters, they actually measure the the wind at 3 meters, and then we extrapolate to 10 meters. So using a larger pond parameterization. So this has actually been compared in the North Atlantic. Was a paper by Theo Clens who compared it to shipboard observations, and I think he was comparing actually to ERA 5 and so on. And so he figured out that, yeah, actually the mini-met is observing the wind. But, people often here, I shouldn't raise my thumb. This is a new GoToMeeting thing. People often, wonder what is a 10-meter wind height when you're in 10-meter waves, right? So this is a problem, even for NDBC buoys that have a wind, observation on it. So the differences that you show, you're worried about the differences with ERA 5 and COAMS TC. So we've discussed that a little bit. COAMS TC sometimes shows the maximum, the gust, the 1 meter gust. We've talked with Jim Doyle and Will, and this may be, sometimes they often peg this to the NHC or the National Hurricane Center winds as well, right? This has to do with their modeling aspect. Now the ERA 5, this is another case of comparing it to a model. It's not a hurricane model. It can't resolve that strong core. And so typically if you just use ERA 5 for something, it's going to be really wide and just not that strong. It's just not resolving that really strong hurricane wind field. So it's natural for it to be low. So the mini-met drifters, we're not observing as high as, say, COAMS TC does. But there could be some reasons, that we're taking a 10-minute wave average. They're doing, the 1 minute maximum, reasons like that. And it's actually been much discussed among the NOPP group as well, because Of course, the wind product is what drives a lot of, the wave modeling and the coastal storms there. So we've only, that mini-met was actually, I think, funded by NOAA. We aren't funding them under the NOPP project at all. But we tend to drop them, when we do these drops to the 53rd, we have other, cases. So the paper I mentioned by Hurricane Michael, there were more mini-mets, wind drifters dropped in that. And we find them fairly, to actually match up fairly well with the model. As you say, when you adjust the 10-meter height and take into account that the coamps may be a little bit stronger just based on their averaging.
Yeah, I asked that question because also we have a buoy, a moored buoy, fixed location observation of winds and currents, ocean currents at 50 isobats on the western shelf. We recorded maximum wind speed at about 3-meter highs because of surface buoy. Of 1 meter mean wind maximums, that's 49 meters per second. In 1 second, maximum is 76 meters per second. So for anybody, whoever analyzed or modeled Hurricane Ian or even Idalian events on the western shelf, we have buoy data available for use. Just advertise for work. Thank you.
Great, thanks, Yonggang. I see, Rick, you've unmuted yourself. I also will note that there's 2 questions in the chat. Isabel, they are both directed at you, so I'll call on you after Rick. Go ahead, ask this question.
Yeah, I've got a question for Jake, and I love to watch how your analysis have been evolving. One of the questions, your wave slope, is this wave slope based on the significant wave height and the peak wave period, for example? And I mean, clearly it's a measure of height and a measure of period from the buoys. And I guess my question is can you compute wave slope from different parts of essentially the spectra? And is there a single wave slope associated with what comes out of the observational data, or are there actually multiple wave slopes depending on what part of the wave spectra you're looking at?
Thanks, Rick. Yeah, so this is actually not just a simple like representative H over representative L. It is an integral quantity. So this is, in this case, the mean square slope. If you're computing from a frequency spectrum, it's the 4th moment. And so in the case of the buoys, we are doing that integral from 0.05 hertz to 0.5 hertz. So that's really the significant number is how high you go in frequency, right? Because those smallest waves are the ones that are going to really determine the mean square slope. So in that case, these are the mean square slopes of the waves down to 6 meters, which I'll note will be a lot different, right? If you go compare those values to something like Cox and Monk, because they're able to really resolve those small waves. But I think in the end, what matters is that you're getting a proxy really right for the shape and the energy in the tail over that frequency range. And so I think the mean square slope from the buoy is sort of really representative of sort of the energy and the shape and the slope of the waves sort of around the equilibrium range and the start of the saturation range. So it is not just one value, it's sort of an average over those frequencies per se. So does that answer your question?
Yeah, I mean, I was just wondering to what extent a spectra has a single value associated with it, essentially, and or again, whether low frequency and or the high frequency. Again, we oftentimes think that the drag is related to the higher, the tails, the higher frequency component of the spectra, and so again, just the notion of whether there's a single representative value for the entire spectra or whether it may vary across the spectrum.
Absolutely. Yeah. Thank you, Rick.
Yeah, I want to add, it's such an important point. I want to add that if you go further and further out the spectrum to the smaller and smaller scales, which I completely agree are, absolutely essential for roughness, those are the kind of things that the radars measure, right? And so a side project that Jake has had is to look at the wave slopes that are estimated from the WSRA that flies on the NOAA P3. So if anyone's familiar with that measurement, it's it's a radar that flies on the Hurricane Hunter and looks down at the surface and returns an estimate of the surface slopes at this kind of centimeter wave scales. And Jake has done this extrapolation method to try to connect the buoy observed slopes, which are spectral and do try to integrate the whole spectrum, to those radar derived slopes, and ends up with something that's roughly consistent between them. I mean, the big picture idea is that the wave slopes saturate at high winds, much the same way we think the drag coefficient saturates at high winds. And that's a consistent story if you then add in these radar products as a measure of the really small slopes. We're sort of building a consistent picture there. And absolutely, Rick, scale matters a lot.
Yeah, that's a great question.
Great. Appreciate the question, Rick, and also the answers, Jake and Jim. I'll turn to Isabel, but for those who may not be able to see the chat for some reason in the audience, we do have two questions for Isabel on the Sofar ocean side of things. The first recognizes that nearshore wave frequency and characteristics are different than those for the deeper ocean, and asks how close to the coastline the Sofar buoy is able to collect data. And the second is focused on the data assimilation scheme being used that Isabel talked about, wondering what the duration of the assimilation window is, what those observations were that were used in the process. So Isabel, I'll turn it to you.
Yeah, so for the first question, we can measure into the near shore, acknowledging that the characteristics of those waves are changing, but the buoy itself is still able to observe. And we have a number of smart moorings in the early years of this project, which is effectively a spotter wave buoy at the surface, but moored. And that's to get the 20-meter water depth observations. And so I think I spoke about that a couple weeks ago. And so we're absolutely able to observe in the near shore, which is really valuable. We're actually shifting to a different observation technique, largely because keeping a mooring within these extreme conditions is really challenging, but not because we can't get observations from those. And there's a number of privately owned smart moorings out there, say around the Caribbean islands, that collect really elevated wave heights during these. I think there was even one in Barrel recently. The other caveat there, as I was speaking to data assimilation and kind of what Jessica was alluding to, is that the wave model that we're running at Sofar is not optimized for coastal wave modeling. And so we're really focused on open ocean wave forecast at this point and need to augment our system to have nested grids, et cetera. For the second question, I can point you to the publication, but at a high level, it's using optimal interpolation, but not on the bulk significant wave height. It's optimally interpolating every frequency bin of the 5 moments from the directional wave buoy. So you have variance density, and then you have A1, B1, A2, B2, and you're basically trying to match or pull the model to all of those components and then recreate a full 2D frequency direction wave spectrum that fits that optimally interpolated directional moments. So I can post that in the chat to explain that more, but the window is actually hourly, which is a little different, I think, than the traditional 6 hourly. And that's because the spotter buoys report hourly. And so the higher frequency cycling leads to higher fidelity. I'll hand it back to you, Alan.
Yep, and while you're looking for that link, which it looks like is right there, for those who might need to grab it before we wrap up, which we're near the top of the hour, so we're going to wrap up soon. There is one last question about whether or not the buoys measure vertical mixing coefficient and upper mixed layer depth as well.
I'll take a stab at that one. Generally, no. I think you're probably thinking of something more like an Argo float or an EM Apex float or a mixed layer float, some that are using a buoyancy engine to do profiling through the upper ocean and provide those sorts of measurements. So generally, everything we've been presenting here, these are surface buoys that are just getting that air-sea interface measurement. And there are plans to have a few of them have T-chains from them and a few variations like that on some of our larger buoys. We put acoustic Doppler profilers and can get some of these things, but that has not been the focus of this project so far.
Great. Thanks, Jim. One last question from Alex. I'll give him license here as we wrap up, but the question is, do drifter OBS yield directional spectra similar to the buoys?
Yes, definitely. I mean, that's what Martha was saying, that, all of these buoys, of the different vendors, different manufacturers, different universities, we have, rallied around the first 5 spectral moments, which have been standard for a long time in wave spectral measurements, going back to the data well wave rider buoys, and NDBC uses them, et cetera. So, the fact that they're drifting does introduce a slight reference frame shift, but that's pretty easy to account for. We know whether you're in a intrinsic reference frame or absolute reference frame, but otherwise, we are definitely all buoys providing very similar products. It's, as a function of frequency, the energy, the scalar energy, and then the first 4 directional moments from which you can reconstruct a spectrum, a full directional spectrum.
Perfect. Thanks, Jim. We are at the top of the hour, so I want to thank everybody for joining us today as part of the NOPP Hurricane Coastal Impacts Forum. As a reminder, this is just one of the multi-part series taking place over the past month and towards the end of this month. Our next session will take place next week, Tuesday, July the 16th at the same time and using the same length. So I encourage you all to join us. And we are hoping that sometime in the August timeframe, we'll be posting a page on the NOPP website, letting you know about the forum and including links to the various presentations for each of the sessions. So until next time, I thank everybody for participating. I definitely thank our speakers for their work and their efforts today, the questions being asked, and of course, our gracious hosts who have allowed us to piggyback on the NOAA seminar series. Have a wonderful balance to your Tuesday, everybody.